Okay, here we're going to look at how to decompose the variance of the stock into market and firm-specific portions. So the first thing that we do is estimated index model. So to remind you, so what we have here is I have the returns on stock C, let's say Citigroup, is equal to alpha plus beta, then I have the returns on the market and the error term. So we're going to estimate this regression model. Again, it's an index model. It's like a CAPM type equation. In many texts you'll see this as the index model. And when we estimate this model, we're going to get three things: an estimated alpha coefficient, beta coefficient, and the variance of the error term, right? So the output of the regression will be these three things. The alpha is going to be irrelevant. We'll see why in a second. But so the idea here is we're going to get this equation with estimated coefficients. And then we just take the variance of this. So in other words, I'm going to take the variance of this side, the variance of the returns on Citigroup, and then the variance of this, the right-hand side of the equation. Now, the first thing to know is alpha, all right, it's a constant. So if I have the variance of a constant is 0, and the covariance of a constant in any random variable is going to be 0. So the alpha drops out, it's irrelevant. And we're left with the variance of estimated beta of Citigroup, returns on the market, plus the error term. So the next thing to do here is to understand, okay, well, the variance, so I have the relevant equation here, the variance of x plus y, these are two random variables. Note, this is the variance of Citigroup, the variance of the returns on Citigroup. Here, this is just another way to write variance, VAR, not value at risk, but variance. It's more convenient, and otherwise I'd have to do a sigma with a small x plus y down there. And so generally, when we write this equation, we just write the variance as VAR. So the variance of two random variables, x plus y, is equal to the variance of x plus the variance of y, plus 2 times the covariance of x and y. In this case, the covariance is going to be of the returns on the market and the error term. And these two are orthogonal, meaning they're uncorrelated. The covariance between the two is 0. At the end of this, because I'll explain why, but for now, you can just trust me that the covariance between the two is 0. So in other words, this term drops out. That term is 0. All right? So what we're going to get is the variance of the returns on Citigroup is the variance of the beta coefficient times returns of the market plus the variance of the error term, right? The only other thing to know is if we have some sort of constant k times a random variable y, the variance is equal to k squared variance of y, right? And that's the last thing we need. So what we get is the variance is the beta squared, the beta here, I have a little hat here just to say that that's an estimated value, but the beta of Citigroup squared times the variance of the market plus the variance of the error term. And this is going to give us, this is the portion of the Citigroup's variance, return variance, right, which is attributable to the market, and this is what's attributable to firm-specific factors. Of course, from this, then you can get the proportion of Citigroup's variance dividing that's due to the market. So by dividing this term by the total variance. And what I'd recommend to take a look at this, and I always recommend getting market data and doing this and seeing if the proportion from market or firm-specific factors is different depending on industry, right? So this is where using sector ETFs is nice. So if you do this for XLF, which is a financial sector ETF, do you get different proportions than if you do this for, let's say, XLE, which is energy? So I definitely recommend doing that. Good. So that explains how to decompose variance into firm-specific and market factors. What I'm going to do here, if that's all you care about, you can stop the video here. I just want to give you a little bit of an intuitive, and what I want to do here is give you a reason to study a little bit of linear algebra, right? So in other words, what I've just told you here is the covariance is 0. Now there's a very easy, if you understand a little bit of linear algebra and what linear regression is when we look at it from a linear algebra viewpoint, it becomes very natural to understand that that covariance is zero. So if you haven't studied any linear algebra, this is just a little bit of motivation to say, okay, well, why don't you take a look at linear algebra, and it'll make regression equations and understanding what's going on in a regression very easy. So from a geometric standpoint, if we, this, I'll just talk about general regressors, x sub 1, x sub 2. So these are my independent variables, and y is my response, it's my dependent variable. And these are vectors. Instead of looking at them as lists of numbers, you can look at them as vectors, right? Again, this is linear algebra, so you might have to look up what a vector is, and I'm going to leave that. But so what happens is, in a linear regression, is we have some subspace, a vector space, which is spanned by our independent variables. So the idea of this is, if I have two independent variables, what this means is I can construct a vector, any vector in this vector space, by changing my my alpha beta coefficients, right? And this is also why you can't have two independent variables that are linear multiples of each other, because then I can't form a linear combination of them. In other words, those two don't span the vector space. I can't construct any vector. I need two vectors which are pointing in different directions in this vector space. And so what linear algebra does is just projects this dependent variable, or y variable, into the vector space that is spanned by our independent variables. And what this does is it makes this error as small as possible, because when it projects it here, right, this is going to be the closest point in this vector space to our point on y here. In other words, if I were to use this as my vector, I was going to choose alpha and beta coefficients to make this as my vector, right? Now I have a triangle, right? So the idea here is this line, this error turn line, is going to be longer, right? So in other words, I have this vector space and I have this triangle. Well, if this is my vector space here, the closest line from my point up here to the vector space is going to be a straight line, straight up and down. So that's why this projection is, we choose this alpha and beta such that it projects it, and then this error is the smallest. But if you notice, this error now has a 90-degree angle. Basically, it's orthogonal to the vector space, which means it's uncorrelated, right? So this has been a little bit, so in other words, once you understand this geometric formulation of a linear regression, it's very natural to say, okay, yeah, these two things are orthogonal, right? This is in the vector space, the error is going to be orthogonal to that vector space. If you haven't studied linear algebra, again, this may not make too much sense, but again, this is motivation for you to study a little bit of linear algebra, because in an afternoon you can start to understand a vector and a vector space, and then this all kind of falls into place, and then for the rest of your life you have at least a mental model of what a linear regression is, which makes ascertaining certain, or remembering certain characteristics about that linear regression makes it very easy. Okay, good. Have a great day.